Well, it was through this man named Muhammad ibn Musa al-Khwarizmi, and I have a difficult time pronouncing it. So that's what it sounds like. Let's do it one more time. So his name is Latinized to algorithmi, and he developed algorithm, which is a technique for doing arithmetic using Hindu Arabic numerals. In 1305, Raymond Lull created a system of logic called Ars Magna, leading to 1642, where Blaise Pascal built the first fully functional mechanical computer. And then in 1692, Gottfried Leibniz refined the binary number system, which is the basis of all digital calculators. In the 1800s came about Charles Babbage, or the father of the computer. He designed the difference engine, which was made to compute polynomial functions. And then he also designed the analytical engine for general purpose computation in 1834. Going to 1843, Ada Lovelace, also known as the first computer programmer, developed Note G in one of her letters back and forth between her and Charles Babbage. And this was a method of calculating a sequence of Bernoulli numbers using his analytical engine. So here's an excerpt from a comic called The Thrilling Adventures of Lovelace and Babbage by Cindy Padua. So you can see them here collaborating and on his analytical engine. And here's a comic which talks about fields by that are arranged by purity and becoming more pure, but computer science is actually not on this comic. So you see here this dog Casper, and he's like, computer science? Well, is computer science just applied math then? So some computer science concepts that were inspired by mathematics. There's algorithms, calculators, binary and functions. But today we're mostly going to be talking about functions and a little bit about calculators. So how do functions differ in math and computer science? So first off, functions in math. A function in math is typically known as a relationship that uniquely associates members of one set to members of another set. Or more formally, a function from set A to set B is an object f, or function, such that every A that's part of a set capital A is uniquely associated with an object f of A, which is part of a set B. So a function in math is therefore a many-to-one or sometimes a one-to-one relationship. So here's a function in math. It's fourth degree polynomial, and here is its solution. So it's quite a long function and quite a long solution. So the solution is fully written out here. It's obviously very difficult to read. This formula is actually too unwieldy for general cases. So typically we create simpler formulas to handle the special cases of this particular formula. Okay, next up is functions in computer science. Sorry for the slides. So in programming, a named section of a program performs a specific task, and that is what a function is in computer science. So in this sense, a function is known as a procedure or a routine. In some programming languages, they make a distinction between a function and a procedure. So a function will actually return a value, whereas a procedure will just do some sort of functionality and return nothing. And here's a function in JavaScript, which I found by searching callback hell. So it does quite a lot. I think it runs a couple of like shell scripts, and it also like writes things to S3. It does a ton of stuff. So that's our function in JavaScript. So between math and computer science, we know that a function is either a relationship and association or a procedure or routine. So again, going back to our quartic function, we see that it describes a relationship or an association of x to the function of x. And here we see from the online etymology dictionary, which is the history of words, that a function was first used in mathematics, probably by Leibniz in 1692, and then first referenced many years later, almost 250 years later, in computer science in 1947. So what happened in 1692? Well, we talk about actually Leibniz notation being created. So Leibniz and Sir Isaac Newton discovered differential and integral calculus. In 1675, Leibniz used integral calculus to find the area under the graph of a function called y, or y is equal to f of x. And then in 1692, when function was first used in mathematics, he was actually the first to employ the mathematical notion of a function explicitly. So he actually wrote this out and wrote that it was called a function. So going back to this definition, what significant event happened in 1947 in computer science? The ENIAC was created, which stands for the Electronic Numerical Integrator and Calculator computer. So the ENIAC was a modular computer. It was composed of individual panels to perform all types of functions. And it actually had these things called function tables. So ENIAC's plug boards were permanently microprogrammed with commonly used instructions that could be referenced from a user program. And user programs were entered as a sequence of instructions into these function tables. And so we see the ENIAC here, and over on the right are the function tables. So I'm pretty sure this is probably where the word function comes from. Okay, sorry. So this is the difference, some notes about the difference between functions in computer science and mathematics. So in computer science, again, they primarily focus on the procedure being performed. And we define functions in computer science based on the output, typically the return value or side effect that we want to happen. And then in mathematics, we primarily focus on defining a relationship between an input and an output. So we define those relationships or functions based on the input or output we're provided. Okay, so now on to JavaScript. So some history about JavaScript. It was created in 1995 by Brendan Eich while he worked at Netscape. And the first standard of JavaScript was written by ECMA International in 1997, 2 years later. The current standard of ECMAScript was created in June of 2018, and they're actually underway in creating the latest version currently. So ECMA International has created these standards, and if you go to their website, they have many types of standards. So JavaScript actually falls specifically under ECMA 262. And if you go back to the standard from 1997, you can see that a math object has always existed in JavaScript. So JavaScript has always had this math object. So JavaScript's math object. If you look at the standard from 1997, I'm not going to try to read all of this, but basically what it says is that the math object in JavaScript is a single object. It inherits from the object prototype of JavaScript. It can't be called with a new operator, so it's not a constructor. And the math object also does not have a call property, so you can't invoke it as a function. Fast forward to 2018, and the standard says almost the exact same thing. So it says it's a global, it inherits from the global object, it's a single ordinary object. It's not a function object, it can't be called with the new property, and it can't be invoked as a function. So they kind of just change the wording around between these two standards. And there are two types of math properties in that object. So there's value properties, which return a number or a value, and function properties, which actually can be called as functions on inputs or arguments. Oops, I went backwards. All right, so the math object in JavaScript has 8 value properties, and I'll go over those right now. But before that, something you'd want to keep in mind with value properties is that they have these attributes. So the first attribute is a value, so the value returned from the value property. Whether or not it's writable, so can you overwrite this object? Whether or not it's enumerable, can you call it in a loop? And then whether or not it's configurable, can you change the attributes of a value property? And within all of these value properties, writable, enumerable, and configurable are all set to false. So you'll see those in a graph in the upcoming slides. So first off, we have math.e. E is known as Euler's number or Napier's constant. Interestingly, it was actually discovered by Bernoulli, so I'm not really sure why it's not math.b. But the number value for E is approximately 2.718. So significant things about the number E. It's actually the limit of 1 plus 1 over n times n as n approaches infinity. And this is actually an expression that arises out of compound interest. So if you're interested in interest, I'd look more into E. And then it's also the sum of the infinite series here, 1 over n, what's the word? Factorial, thank you. It was like exclamation point. So next up are the logarithms that exist under value properties. And so in mathematics, I couldn't remember what a log was because I haven't done math in many years, but essentially a logarithm is the inverse function to exponentiation. So in other words, base b log of x is equal to y, and then b to the y is equal to x, or more in easier terms with numbers, base 2 log of 64 is equal to 6, or 2 to the 6 is equal to 64. All right, so the next up, we have the natural log, which actually is a base e log of a number. So the natural log of 7.5 is equal to 2.0149, or e to 2.0149 is equal to 7.5. So in other words, base e log of x is equal to the natural log of x. So in JavaScript, we also have a value property, natural log of 10. And we also have the natural log of 2. And then we have the base 10 log of e. Interestingly, base 10 log of e is approximately equal to the reciprocal of the natural log of 10. So for those of you who don't remember, a reciprocal is just taking 1 over a value. And then similarly, we have base 2 log of e. And the value of base 2 log of e is approximately equal to the reciprocal of the natural log of 2. And then we also have pi, which we know is the ratio between the circumference and the diameter of a circle. And actually, in the US today, it's Pi Day. It's March 14th. We also have the square root of 2 and the square root of 1/2. And interestingly, with those are also reciprocals of each other. Okay, so let's see if I can get this demo time to work. Okay. Can you read that? Okay. So first thing I do here is I just print out the number e. Did I hear a no? Should I zoom in more? Is that good? Okay. So the first you see here is e, and then I actually print out the natural log of 10 below. So interestingly, if we scroll over here, what I do here is I take the natural log of 10, and then I do e to the natural log of 10 here. So you'd expect that these are equal because taking the natural log or the e of something should actually just equal that number. But here you can see in JavaScript, and actually interestingly in IE versus Chrome. So in Chrome it actually is 10.000002 instead of 1, but here I'm actually doing it in IE and it's different. So I think between different browsers you see that JavaScript math is inaccurate between those two browsers. And then similarly, if you look below here, we take e to the power of the natural log 2, and you can see we are expecting 2, but we get 1.9999997. So it's off by about 3 to the 10 times 10 to the negative 16th power or so. Next here we have base 2 log of e. And if we remember from before, the reciprocal of the natural log should be equal to that. So these two numbers should be equal. And if I scroll over here, we can see that they are. And then if I get the reciprocal of the base 2 log of e, we should expect to see the same value as the natural log of 2. So you can see these two here are equal. And then I just, for sanity's sake, took the difference between those two to make sure that they were equal. And they actually are at least equal in this browser. And then I did basically the same thing with the natural, or base 10 log of e, and then the natural log of 10. So we can see that this value and the reciprocal of the natural log of 10 are equal, about. They're very close. You can see that they're actually off by about one significant figure here. And then, interestingly though, if you actually take the difference between the two, it's 0. So math is pretty finicky, at least with the value properties in JavaScript. Okay, so back to the slides. So just in a quick review, e to the natural log of x should be equal to x if x is greater than 0, or the natural log of e to the x should also be equal to x in that case as well. Base x log of e should be equal to the reciprocal of the natural log of x, and the natural log of x should be equal to the base x log of e. So JavaScript math precision by observation, it's not so great, and it differs between browsers, so something to keep in mind. And it's typically accurate to about 15 or 16 significant figures. Okay, next up, function properties. So JavaScript came with 18 function properties, so quite a few. I'm going to go through them pretty quickly. Something to note is that JavaScript standards, under all of these function properties, are listed special cases. So under those special cases, they talk about what happens if you feed in nan, positive or negative 0, positive or negative infinity, and then positive or negative numbers. But I'm not going to include them here because they're quite long. So first off with math.abs. So math.abs returns the absolute value of x. So basically the distance or the magnitude of x. So the distance from 0. Next is the arc cosine, which I'll get into a little bit later. It's like a trigonometric function. It's much easier to grasp in my mind if you can graph it actually. And then we also have arc sine. We have arctangent. We have arctan2, which actually runs the arctangent on the ratio of y to x, the quotient of y over x. And you can see here arctangent2, interestingly, has a lot of special cases. So this is one of the few I listed. We actually have 3 slides of special cases for arctangent2. So if you happen to use that in JavaScript, keep that in mind. We also have math.ceil, which essentially rounds up to the nearest integer. And interestingly, if you run math.ceil, it's equal to the negative floor of negative x. And then we have cosine. And we have math.exp, which I expected to be actually running a power, essentially exponentiation of 2 integers, or 2 numbers. But it actually raises e to the power x instead. Let's see, this one I think is math.floor. So math.floor is also equal to the negative ceil of negative x. Something I was wondering is if we have math.ceil, why didn't we call it math.basement? Probably because the meme was created before or after JavaScript was created. Okay, next is math.log, which again I thought was just going to be running log of 2 different numbers, or a base number log of another number, but this is actually running the natural log of x. And then we have math.max, which interestingly, something to note, it runs 2 number on every input within the function, and then it will take the max of that function. And similarly, min will return the minimum of the inputs. And then we have math.pow, which is what I was actually more expecting from math.exp. But basically all it does is run the star operator, or runs an exponentiation of 2 numbers. And here I should have mentioned earlier, but you'll notice that many of these functions talk about the implementation dependent approximation. So they get into that a little bit later in the standards. And we see here with the star operator, there are tons of special cases as well. Okay, next we have math.random, which returns a number between 0 and 1. And then math.round, which actually rounds a number to the nearest integer instead of rounding up or down. And we have sine, and we have the square root, and we also have tangent. Okay, so demo time of these guys. I kind of skipped over the trigonometric functions because I want to graph them later. Let's see. Okay, so first off, I just print out a bunch of random numbers. If you reload the browser, it'll actually print out a bunch of more different random numbers. I'm just going to delete this so I can get it out of the way. Next, we can see the absolute value of 2 and then the absolute value of negative 2. And you'll see that they're both equal to 2 here. The next one I run is actually, I was curious if running the function property of square root of 2 would be equal to the square root of 2 value property. And I can actually see that they are accurate, at least in this calculation. And the same goes for the square root of 1/2. So you see here I run the function property and then return the value property down here. Okay, next up is seal and floor. So you can see here I'm running the seal of 3.5. And then I run the negative floor of negative 3.5, which returns the same thing. And then I do the similar thing, or a similar thing, but opposite, math.floor versus the negative seal of negative 3.5, both of which return 3. And then just to check out round, I wanted to get a sense of whether it's going to round things up or round things down. So you see that if you round 3.5, then you'll get 4. But with negative numbers, it'll actually round down because, or it'll round up to the negative number. So it'll be negative 3 instead of negative 4. And then next up we have e squared. So here I actually run an arithmetic function, or the arithmetic operator, so e star star to squared. And we can see if I run the function property exp, so e to the 2, or e squared here, you can see that they're actually off, again, by a couple of significant figures. So I found that pretty interesting as well. So interestingly, the arithmetic operator has more accuracy than the functional property. And then here I do a similar thing with the log function property versus the natural log of 2. And you can see here, interestingly, these actually are both accurate and the same. And the same goes for log of 10 versus the value property of the natural log of 10. And then below here, basically just trying to run the math function, pow. So I'm just going to scroll over. So you can see I'm running pow 23 to 2.3. Or, yeah, I think that's right. Yeah, 23 to the power 2.3. And then I also run it again using the arithmetic operator, so the star star operator. And you can see that those two are equal as well. And then lastly, what I do is I'm running the min and max on both strings and on values. So again, something to keep in mind is that with max and min, it'll run 2 number on each of the values before evaluating. So math is weird in JavaScript, and strings are numbers also. Okay, so back to this. Okay, so in June of 2015, ECMAScript's version 6 was released, better known as ES6, and we actually gained a bunch of functional properties. And when I say a few, I actually mean that we gained 17. So they actually doubled the number of functional properties in JavaScript's math object. So we have the hyperbolic arc cosine. We have the hyperbolic sine. We have the hyperbolic tangent, arc tangent. And then we have cube root. So in addition to square root, we now have cube root. This one is interesting. It's CLZ32. In the standard, it says it runs this set of steps, which is kind of long. So in layman's terms, what it stands for is counting the leading 0 bits of a 32-bit representation of a number. So essentially the reason for doing that is because it's useful for systems that compile to JavaScript that run with 32-bit numbers instead of 64-bit as JavaScript does. Then we have the hyperbolic cosine. We have exp m1, which is essentially e to the x minus 1. Then we have math.fround, which again runs a set of these steps, but in more layman's terms, actually what it does, it returns the nearest 32-bit single precision float representation of a number. So as I was saying before, JavaScript uses 64-bit double floating point numbers internally. So it offers very high precision when it's creating numbers. But when you're working with 32-bit floating point numbers, math.fround is helpful because it will cast the 64-bit floats into 32-bit floats to be used in other languages. So I'm like frowning basically because I'm a 64-bit number instead of a 32-bit one. Next is math.hypot, which essentially returns the hypotenuse. So it returns the square root of the squares of the numbers fed into it. And then we have math.emule, which again runs a set of steps here. But from Mozilla Developers Network, essentially what it does is it returns the result of a C-like 32-bit multiplication of two parameters. And then we have log1p, which runs the natural log of 1 plus x. And here we have log 10. So earlier I was saying I expected log to be a log of any base, but here we actually finally have base 10 log. And we also have base 2 log as well. Then we have the sine, which returns the sign of a number. So it'll return 1 for a positive number, -1 for a negative number, and 0 for 0. And then we have the hyperbolic sine, the hyperbolic tangent, and trunc, which returns the integer portion of a number by truncating the floating point portion of it. Okay, next demo time. Okay, the first thing I do is I just return a cube root of 6, which comes out to about 1.81. The next thing that I run is CLZ32. So if I run CLZ32 on 1,000, you can see it returns the number 22 here. Another way of doing that is you can actually cast 1,000 to binary representation by running toString and then grabbing the length of that. So if you do 32 minus that number, it'll actually return to you the number of leading zeros, which matches. Okay, I've got about 10 minutes left, so I'm going to try to go through these more quickly. Okay, so a note about that one function is it's actually going to only work on positive numbers. So next we have the exp m1, and here I do exp m1 using the functional property, and then I call it explicitly by running exp2 and then subtracting 1, and you can see those numbers are equal. But again, this value property has more accuracy in terms of significant figures. Similarly here, I run log1p of 2, and then I also run log 2 plus 1, so log of 3 essentially. And you can see that those two are the same here. Next is I run the base 10 log of e, and then I actually choose to use the value property to see if those are the same, and they are. And the same goes for base 2 log of e, as well as the, let me scroll down here, the value property here. And then we have math.fround. So interestingly, math.fround, if you see, there's math.fround of 1.5 is equal to 1.5? And you'll see that that's true. However, with math.fround of 1.337, is that equal to 1.337? And that's actually not true. And the reason is that 1.337 cannot be precisely represented in binary. So it actually differs between 32-bit and 64-bit numbers. Next up is hypot. So again, I just run the functional property versus running the square root property, and then using the star operator. We can see those numbers are equal here. And then I run a mule on a couple of numbers here. So the mule of -5 times 12 is equal to 60. And then I actually can run a mule on hexadecimal representations of 32-bit integers as well. So this is essentially saying -2 times 5. And that works as well. And then the last couple we see here are running sine, so returning the sine of different numbers, and then the truncation of a few of these numbers as well. So you see it returns an integer. And the last couple of things that I didn't mention is that hyperbolic cosine, sine, and tangent will actually be equal to expressions using e. So here what I've done is I've actually checked to see if that's true or not. So you can see, for example, the first one, we have a hyperbolic cosine of 1. So that's equal to e to the 1 plus e to the -1 divided by 2. And if I run those functions, you can see that those are all equal as well. Okay, so that's the end of functional properties 2 demo. So earlier I was talking about the implementation-dependent approximation, and this is actually where it comes in. So in the standards of ECMAScript, essentially they're saying that, for argument's sake, the functions in the math object are intended to compute approximations, and some latitude is allowed. So we already know that JavaScript is not super accurate with math, but they actually write it into the standards to say oh hey, some latitude is allowed. I'm just going to skip that slide. But basically, what they're also saying is that they use fdlibm, which is the freely distributable libm. It's a C math library for machines that support IEEE 754 floating point arithmetic. And so that's the standard that JavaScript standards use. Okay, last demo time. So I didn't have time to create a JavaScript calculator myself, but I actually found that there are a couple on the internet already. So the first one is Grapher. And so you can see here, we can actually put in the quartic function. Oh, I can't type on this. Maybe I can try to copy from my notes. Okay, so here's the quartic function, which we were looking at earlier. So I found this one particularly interesting because it has such a complicated solution, but if I just graph x squared compared to it, they're pretty similar. So I cannot highlight. Okay, so here you can see they're actually pretty similar. And if you zoom out using Grapher, you can see how they differ here. So one thing to note about Grapher is I was actually trying to use it with the functional properties of JavaScript or ECMAScript, and it actually didn't work. So I kept looking for more graphing calculators, and I actually found Graphy, not to be confused with Raphy. So here's Graphy. So Graphy is pretty cool because what you can do is you can actually feed in any type of function. The only problem is I noticed that it actually only takes one input. So if I want to run, for example, arctangent 2, I'm not able to do that with Graphy. So let me just copy over some of our trigonometric functions. Okay, so you can see here we have sine and cosine and the tangent graphed. So I'm running a bit out of time, but essentially what I have more is like the graphs of all of these other trigonometric functions to get a sense of what happens, and Graphy will actually graph them all accurately as well. So essentially, in conclusion, how much math can you actually do with JavaScript? Surprisingly, you can actually do quite a bit of math with JavaScript. So functions are different between math and computer science, and you can use functions to do graphing with JavaScript, but mathematical precision is, again, not so great with JavaScript. And if you haven't got enough of math, something to note is that the CSS working group is adding a ton of math to their standard pretty soon as well. So check that out if you want more math. And Casper is basically like, wow, you can do a lot of JavaScript with math. It's just not so great with precision. And that's all I have. Thank you.